Good morning, students. My today's lecture is on Ellingham diagram, and Ellingham diagram is a very important topic in this chapter. Now, before we start this Ellingham diagram, I must make you understand that the various metallurgical operations are based on the knowledge of our thermodynamics. We have studied two equations in thermodynamics. If you recollect, one is delta G is equal to delta H minus T delta S, and another equation is delta G is equal to minus 2.303 RT log K. Now, when we bring about reduction of metal oxide, what happens? Metal oxide splits to give metal and oxygen. So if you look at the equation carefully, entropy increases, that is delta S is positive. Now delta S positive makes the value of delta G negative. Now to further increase the feasibility, the possibility of the process to occur, if we raise the temperature T, then definitely the value of delta G will become more negative, because T delta S factor, it will become greater than delta H. Okay, so from this what we understand is that when we have to bring about reduction of metal oxide, we must raise its temperature. And the second thing, now if the value of delta G for a process is positive, then this reaction, as we know from thermodynamics, will not occur. The process will not be spontaneous. But we can make it spontaneous. How? We can couple this process, this reaction, with some other reaction whose delta G value is very large. So large so that when we combine the two reactions, the overall value of delta G for these two reactions becomes negative. So we can bring about a non-spontaneous process just by mixing the two reactions, by coupling the two reactions. This is called coupling of reactions. Now, for taking all these decisions, we need to take the help of a diagram which is known as Ellingham diagram. This we will discuss right now. Yes, students, now we have to understand what is Ellingham diagram. You can have a look on the Ellingham diagram given along with. You will see that it is a diagram consisting of certain graphs or certain plots. These graphs are between two things: delta G naught F, that is standard free energy change of formation, versus temperature for the formation of various oxides. So what is the Ellingham diagram? Sir, Ellingham diagram consists of various plots or various graphs between delta G naught F and T for the formation of various oxides. Now, what are the salient features what you observe in this Ellingham diagram? Now, Ellingham diagram, it consists of various graphs. These graphs are between delta G naught F versus T, and they are for the formation of oxides. Now, if you see an equation representing formation of a metal oxide, suppose 2 moles of metal, they combine with 1 mole of oxygen gas and forms 2 moles of metal oxide, right? Then delta S is negative. In this case, delta S is negative because entropy is decreasing. Therefore, the value of delta G increases with the increase in temperature. The value of delta G increases with the increase in temperature, according to Gibbs-Helmholtz equation. That is, delta G is equal to delta H minus T delta S, right? Now the second point which you have to see is various plots in this diagram are straight lines. The graphs which you are seeing, they are in the form of straight lines, except at certain places. What happens at these places? At these places there occurs a sudden change, an abrupt change in the slope on the positive side. Now why these abrupt changes occur? It is because there occurs a change in the phase of the material. That means either the material is getting, solid material is getting converted into liquid, or liquid is getting converted into gas. So what happens then? Then the entropy increases. Then the entropy increases. So the straight line graphs, if they abruptly change their direction towards the positive side, it means entropy has increased. The third point, there is a point in the curve below which the value of delta G naught is negative. If you look at any curve, there is a point below which the value of delta G naught is negative. So what does it mean? It means that this is such a temperature below which the metal oxide is stable, and above such points, above such temperatures, the metal oxide is unstable. So if the temperature is raised above these points, then what happens? The metal oxide becomes unstable and decomposes of its own. So the next point is this, that this diagram has graphs for delta G of oxidation of common metals. And if we reverse it, we can say that these are the graphs for reduction of metal oxides. Okay, if we reverse it, and then there are graphs of certain other reducing agents also. So you will see I've already listed the various metals, and they are getting converted into their oxides, and the graphs are for them. And also the graphs of certain reducing agents like carbon monoxide, etc., they are also given. Now such diagrams also exist for the formation of metal sulfides as well as metal halides, right? It becomes clear from these diagrams, that means the Ellingham diagrams for metal oxides and metal halides, it becomes very clear from their diagrams that why the reduction is difficult. Actually, it is very difficult to make the delta G naught negative, right? So, but in metallurgical operations, I've already told you, it is easier to bring about reduction of metal oxides rather than metal sulfides and metal halides. Is it clear now? Then what is the role of reducing agent? Supposing we want to bring about reduction of a metal oxide, then we mix along with this some reducing agent. Now if somebody asks you what is the role of reducing agent, the role of reducing agent is nothing but to provide a very large and very high negative value of delta G for the reaction. So when we couple this reaction with the reaction for reduction of any metal oxide, the overall value of delta G becomes negative and the reduction becomes possible. Okay students, now I will like you to have a look on this Ellingham diagram. Now along the x-axis temperature is taken, and along the y-axis the value of delta G naught F, that means standard free energy change for the formation of oxides, is taken. So you will see that there are various plots for the oxidation of silver, mercury, copper, iron, zinc, chromium, aluminium, magnesium and calcium, etc., right? And also there are graphs for oxidation of carbon and carbon monoxide, which act as reducing agents. Students, now let us understand what are the applications of Ellingham diagram. Ellingham diagram helps us in predicting whether the thermal reduction of a given ore is possible or not. Okay, we can find out whether we can bring about thermal reduction of a given ore or not. The second thing, Ellingham diagram helps us in choosing a suitable reducing agent. That means with which reducing agent we should bring about reduction. It also helps us to have an idea about the temperature at which reduction of metal oxide can be carried out. And further, another thing which we understand from Ellingham diagram is why the rate of reactions become faster if the ore melts down. Okay, if the ore melts down during reduction process, why the rate of reaction becomes faster. So these are the applications of Ellingham diagram. Now, what are the limitations of Ellingham diagram? So the limitations are, Ellingham diagram only informs us whether the reduction of given metal oxide will occur or will not occur. Okay, so it tells us whether a reaction will take place or not. It does not give us any idea about the kinetics of that reaction. That means whether the reaction will be fast, whether the reaction will be slow. Okay, so it does not tell us anything about the speed of the reaction at which the reduction or reaction will take place. Another limitation, which is a limitation of thermodynamics itself, is that this Ellingham diagram is based on the fact, it is based on an assumption that reactants and products, they are in the state of a chemical equilibrium. But during the processes, the state of the reaction is never the state of chemical equilibrium.